Modern language models answer hard questions with impressive fluency, but that fluency masks a fundamental instability. A single forward pass is a fast, fluent, and unreliable problem solver. It is right often enough to be useful, and wrong often enough to be dangerous. In production, where a wrong answer carries real cost, we cannot rely on average performance. We need systems where answers are trustworthy at a known cost. The answer isn't just a better model. It's organization. Maestro Order is a model-agnostic orchestration harness that turns unreliable solvers into reliable problem-solving systems. It does this by composing models according to 4 structural primitives: Decompose, Ensemble, Verify, and Recurse. These are managed by a budget-aware controller that decides exactly where to spend compute, allocating verification, and voting to the stages that offer the highest marginal reliability per unit cost. Let's dive into how this works, the reliability laws that govern it, and the engineering required to make it robust. The core insight is the generate-verify asymmetry. For many tasks, checking a candidate is far cheaper and more reliable than producing it. Whether it's running unit tests, re-evaluating math, or searching for a counterexample, verification provides a high-leverage mechanism for amplification. Maestro Order exploits this by treating any model as a black box base solver behind a uniform interface and layering a verifier ensemble on top. The architecture is built around a few key components. First, the solver interface. Every component exposes solve, task, CTX, returning an answer, a self-reported confidence score, a trace, and the realized cost. This uniformity allows the controller to treat a whole subtree of computation as a single solver. Second, the blackboard. This is a shared, structured record of state, traces, and verifier verdicts. It's the unit of observability and replay. Because every call is attributed to a stage, we can reconstruct exactly what happened. Third, the solver pool. This provides the diversity needed for voting. A pool of near-identical solvers votes poorly because their errors correlate. The pool composition is the primary control on error correlation. Fourth, the verifier ensemble. This contains checkers ranging from deterministic tools, like type checkers and execution sandboxes, to model-based critics. Each verifier returns an accept or reject decision with a score. Fifth, the controller. This is the brain of the system. It makes per-instance decisions on how to spend a compute budget across decomposition, voting, and verification. The controller is guided by the odds law, a reliability calculus that describes how these primitives compose. The most important result is that a verification gate multiplies the odds of correctness by the verifier's likelihood ratio, lambda. Lambda is defined as beta over alpha, where beta is the completeness and alpha is the false acceptance rate. If you have a base solver with a correctness probability of 0.55, that's a log odds of roughly 0.2. If you apply a verifier with lambda of 6, you add log 6, which is about 1.79 to the log odds. The new log odds become 1.99, which corresponds to a probability of 0.88. Apply a second gate, and you're at 0.978. 4 gates get you to 0.999. This is geometric amplification. Each gate multiplies the odds, so reliability grows exponentially with the number of gates, provided the verifier maintains discrimination. Now let's compare this to voting. Self-consistency samples diverse candidates and takes the majority answer. This works well when per-sample correctness exceeds 0.5 and errors are diverse. However, voting is bounded by a correlation floor. If solvers share blind spots, adding more votes yields diminishing returns. In simulations with a Gaussian copula latent factor introducing error correlation, voting plateaus far below 1, regardless of committee size. The controller navigates this by estimating the marginal log odds gain per unit cost for each mechanism. It implements a greedy approximation of the water-filling optimum. It spends the next unit of compute on whichever stage currently offers the largest reliability gain. In practice, this means the controller prefers verification when a discriminating checker exists. A single gate with lambda of 6 can outperform dozens of votes for a near-threshold solver. The controller detects the regime it's in from measured marginal rates, rather than committing to a fixed pipeline. Let's look at the results from a faithful Monte Carlo simulation of the harness over a parameterized solver verifier model. With a weak base solver at 0.55 and a robust verifier with lambda of 6, verification reaches 0.98 reliability within 8 calls. Majority voting on a slightly better solver at 0.62 needs about 90 calls to pass 0.99. The cost difference is an order of magnitude. The controller's trajectory follows the steepest slope. From a base of 0.55, the first verification gate offers about 0.64 log odds per call, while extra votes offer only 0.05. The controller chooses gates from the start. Voting only becomes the better first move when the verifier is weak, or the vote margin is already large. Abstention also plays a critical role. By committing only when the accumulated log odds score clears a calibrated threshold, the harness can abstain on hard cases. This trades coverage for reliability. In simulations, committing only on the most confident 20% of instances drops the error rate from 0.45 to under 0.1. This is selective answering, and it's the cheapest reliability available when full coverage isn't required. For this to work, the system must honor a set of invariants. These are the contracts that make the reliability laws apply. Invariant 1, confidence is calibrated log odds. Every commitment carries a confidence that, after calibration, represents the true log odds of correctness. Raw scores are never used for decisions. They're wrapped by a calibration map, like isotonic regression, fit on held-out data. This makes gates composable, because gates add to log odds, and abstention thresholds them via Chow's rule. Invariant 2, fail closed. Any ambiguity, a tool error, a timeout, or a malformed candidate is treated as a rejection. Never as a silent accept. This keeps the false acceptance rate bounded by the verifier's genuine error, not by infrastructure flakiness. A harness that fails open would see its lambda collapse under load exactly when reliability matters most. Invariant 3, monotone confidence. Adding work never decreases the system's information. A new vote or gate can only sharpen the posterior. The controller never discards evidence. This guarantees that spending more budget weekly improves reliability, so the cost-reliability curve is monotone. Invariant 4, budget conservation. Every call is attributed to a stage and counted against the budget before it is made. The controller cannot overspend. Reliability claims without cost are meaningless, so the two are always reported together. Invariant 5, determinism up to declared randomness. Given fixed seeds and back inversions, a solve is replayable bit for bit. Randomness enters only where declared. This makes experiments reproducible and regressions diagnosable. The engineering of verifiers deserves special attention because verification is the high-leverage mechanism, and gameable verifiers are the dominant failure mode. The goal is high discrimination that is robust. It must hold even when candidates are produced by a process optimizing for acceptance. Prefer ground truth checks. The most robust verifiers reduce to executing a specification. For code, run the candidate against unit tests, property-based tests, and sanitizers in a sandbox. For math, reevaluate numerically or machine check a proof. For facts, corroborate against retrieved sources. The defining property is that their false acceptance rate is bounded by the specification, not by how the candidate was generated. When only a model can check, make it as robust as possible. Ask the judge to find a counterexample rather than rate quality. Refutation is harder to game than approval. Require the judge to show its verification chain and verify that. Use a judge independent of the generator to keep errors conditionally independent. Combine several judges so a single exploitable blind spot doesn't dominate. Measure lambda online. Do not assume it. The controller maintains running estimates of beta and alpha from instances where ground truth is later revealed. Verifiers whose estimated lambda drifts toward 1 are demoted. This is an explicit guard against verifier gaming. Under sustained optimization, a verifier's effective alpha tends to rise as generators discover what it wrongly accepts. This is Goodhart's law. The harness watches lambda over time. When it drifts, it reduces that verifier's weight, rotates in fresh checkers, and raises the abstention threshold. Disagreement among diverse verifiers is a cheap early warning signal. A sudden rise in unanimous acceptance with falling downstream correctness is the signature of a gamed gate. Decomposition is the riskiest combinator. By the serial law, it can only lose reliability unless each boundary is restored by verification. The planner is conservative by design. It decomposes only when the split is clean and checkable. Each subtask boundary is annotated with the verifier to apply on recombination. Type compatibility is checked statically before any model call. The recombination step is itself a gated solver. This is the recursion master theorem realized. Depth is affordable precisely when every level is gated. Let's look at deployment profiles. The harness specializes to different tasks by changing only the solver pool and verifier ensemble. For grade school math, the base solver samples chain-of-thought solutions. The verifier ensemble includes a deterministic arithmetic reevaluator, a units checker, and constraint substitution. Because these checks reduce to executing the problem's definition, lambda is high. The controller leans heavily on gating. For program synthesis, verification is nearly ideal. The verifier executes the candidate in the sandbox against tests. Execution-based checking has very high discrimination. The controller's dominant mechanism is a single high lambda gate plus refinement. On rejection, the failing test output is fed back as a critique, and the solver revises. For open domain question answering, verification is hardest. The harness leans on grounding. The solver must answer with citations, and the verifier checks corroboration. No single check is decisive, so the controller combines a modest verifier panel with self-consistency and sets a conservative abstention threshold. The system answers confidently where sources agree and abstains where they do not. Adaptive allocation beats fixed pipelines. A fixed pipeline, like always sample 5 and verify twice, spends the same budget on every instance. It overpays on easy cases and underserves hard ones. The controller reads each instance's running log odds and stops early when the target is met, redirecting budget to instances that need it. Because difficulty is heavy-tailed, this adaptivity is where much of the practical cost saving comes from. There are failure modes to manage. We covered verifier gaming. Correlated errors limit voting. Decomposition error compounds if boundaries aren't gated. And cost must be managed. The controller's budget cap and abstention keep total cost bounded. Caching and parallel fanout keep latency manageable. Reliability is not a property of a model. It is a property of how models are organized. Maestro Order demonstrates that by compiling 4 structural combinators into runtime components and using a budget-aware controller, we can reach reliability targets at a small fraction of the cost of voting alone. Verification amplifies reliability geometrically. Voting is a cheap supplement bounded by diversity. Abstention converts confidence into reliability. The practical message mirrors the theory. Build robust checkers, diversify solvers, verify every boundary, and let the controller allocate at the margin. The full source code, simulation, and reproduction scripts are open source. You can regenerate every artifact, figure, and table with a single command. Reliability is measurable, reproducible, and engineerable. If you want to dive deeper into the reliability calculus and the odds law, check out the companion report. And if you're building systems where wrong answers are not an option, it's time to stop relying on single forward passes and start organizing intelligence. Thanks for watching.